So we resume today with David Kosower's fourth and final lecture on loop level technology.
Thanks. So I see that a certain fraction of your colleagues did not come back after drinking beer yesterday. I hope they're not sleeping off too severe a hangover. In any event, in the first few lectures, we saw how to derive a new style of master equation, and then we saw how to use the analytic structure of the amplitudes in order to find some equations for the coefficients, the rational coefficients in that representation. We looked more specifically at one box integral in that representation. Of course, when you're doing a calculation of an amplitude, there's many boxes, and you can figure out just from knowing the external particles which boxes could possibly appear there. And then there are triangles and bubbles, and then there are rational terms. I'm not going to go through in detail. I mentioned briefly in response to a question at the end of yesterday's lecture how you would go about doing that. I'm not going to discuss any of that in detail. The other thing I'm not going to really have time to do, but in some sense a lot of the ingredients we've already seen, is that we've looked at it in terms of the integrals, but one can also think about manipulating just the integrands, and there again one can do a decomposition, and there are some differences. But one can do a decomposition, and then one can use unitarity to fix the coefficients of that decomposition, and those coefficients are essentially equivalent to the rational coefficients that we were finding by this generalized unitarity procedure. And to date in the literature, that second approach of looking at the integrands is the way that one would proceed to do two-loop computations. There's a certain amount of additional technology related to a subject called computational algebraic geometry that one would need to understand in order to go on to two loops. And I decided not to embark on that because I'm afraid that one lecture would not really be enough. There's a whole other set of subjects which is having to do more with the structure of one-loop amplitudes. Once one has calculated them, you're trying to check things, you're trying to understand the general properties, and that's what I wanted to talk a little bit about today. So we're going to look at the singular behavior in a very general sense of singularities of amplitudes, and we're going to focus on loop amplitudes. We're going to go back and look a little bit at tree amplitudes because Professor Hen didn't quite cover in the detail that I expected some of these issues. So he mentioned the fact that there are certain limits of external momenta, collinear, soft, when there's certain universal factorization behavior. So that's one kind of singular behavior we'll look at in terms of certain regions of the external momenta, if you think of now varying the external momenta over all possible configurations. And the other has to do with the fact that we're using dimensional regularization, and as I've been stressing from the very beginning, everything we're dealing with here is divergent as the dimensional regulator epsilon is going to 0, and we have the ultraviolet divergences which from our current point of view are a little bit trivial, and the infrared ones which are a little bit more intricate, and that's what we need to understand a little bit more. So, and the other thing that we'll do for a change today is to do just a little bit of really physics rather than just quantum field theory. We're going to try and understand some of the things that you're doing. So, in fact, as I mentioned in the very first lecture, one of the important applications of the scattering amplitudes technology is to the calculation of differential cross-sections for experiments. And today that means mostly the LHC, but historically it would have also meant E plus E minus, and for a variety of conceptual reasons, E plus E minus is the simplest thing that we can think about. And in fact, the very simplest process you can look at high energy plus E minus colliders is the production of two jets. And the very simplest approximation to the production of two jets is a process where you have E plus E minus producing a quark anti-quark pair. So we all know how to write down the Feynman diagram for it. This is a simple enough process that you could even do the calculation this way on the back of an envelope. Of course, you can also use VCFW, and that's a good exercise. So in the real world, we would have either a Z or a photon being exchanged. And let me call this amplitude A2, the 2 standing for the 2 final state partons. So, and of course, their differential cross-sections are really what people ultimately measure. You can't measure a total cross-section because you'd have to have a 4 pi coverage. And you can imagine if you were standing in the beam direction and looking at the collision point, well, that would actually be a very bad idea because the beam would blow your head off. But if you were to put a detector in that place, it would burn out the detector. So there's necessarily holes in coverage. So you actually have to calculate fiducial, what are called fiducial cross-sections. But we're going to ignore that issue for the moment. And so the simplest thing we can imagine calculating is the total cross-section. And there's some set of constants having to do with the couplings and various factors of pi and things like that, which I'm not going to worry about. And we have an integral over the phase space, and then we simply take this matrix element squared. So that's our total cross-section. And that's a simple enough calculation. It's even entrusted to people taking their first field theory course. So the next simplest process, well, you could think of maybe producing E plus E minus or mu plus mu minus, but let's just focus on hadronic final states. The next simplest process would be producing 3 jets. So instead of 2, we have 3, and then the simplest approximation to that would involve adding a gluon to the final state. So then we would be looking at the process E plus E minus to QQ bar glue. It's the simplest approximation, and this is already a process where you could do it by Feynman diagrams, but it would actually be simpler to do it by modern technology. In any event, we're not actually going to worry too much about the actual details of the calculation. So there are a variety of invariants we have here. We have S E plus E minus, S Q glue, S Q glue Q bar. Let me imagine. So we haven't really talked either in Professor Hand's lectures or in my lectures about the color decomposition when you have objects in the fundamental as well as in the adjoint, but there is one. And you can imagine that one of the color orderings you need to think about is precisely this ordering of the particles. It's going to be convenient to introduce some scaled invariants just so we can think a little bit about dimensionless quantities and not worry too much about keeping track of dimensions. So let me call S the center of mass invariant. That's, of course, conventional, E plus E minus. And then there are various other invariants, as I say, for example, Q bar glue, and so on and so forth. So the first thing that we might be inclined to try to do is to calculate the total cross-section. I mean, we're going to ignore the fact that there are holes in the detector and beams and things like that. And so you might think, well, let's just calculate the total cross-section for 3-jet production. Some of you already know where this is going, but don't whisper to your neighbors. For some people, it's probably the first time they're seeing this. So, this amplitude is going to be A3. Of course, I'm including, from a Feynman diagrammatic point of view, I'm including the 2 different diagrams that arise here. If I do it by BCFW, that just You just get that for free. So again, there are various constants which I'm not going to keep track of. The squared matrix element. And here it's simple enough one can actually write it out in terms of the invariance, the scaled invariance. It's something proportional to some polynomial in the numerator. And as you might expect, it's symmetric in Q and Q bar. But really what's more interesting for us is the denominator. So I think everyone for this process probably knows what the integration region is. It's the Dalitz triangle. And the Dalitz region is complicated if there are masses, but when we just have massless particles, it's quite simple. We just have an integration over the triangle defined by these scaled invariants. Some of them is less than 1. So, I think you can see already that we have a problem. Who does not see that there's a problem? Who does see that there's a problem? Some people are still asleep, I see. Okay, so if we just go ahead and integrate, so again there's some constants which I'm not keeping track of, integrate over the Dalitz triangle, over the two invariants or scaled invariants, then we can see that we are going to get infinity. Because we're integrating 1 over y all the way down to y equals 0, and that's a logarithmic integral. If I didn't go all the way down to 0, then when I take the argument of the log to 0, I just get infinity. It's a logarithmic singularity. Well, sort of mechanically, we can go back and look at the integrand, and of course we identify the source of the problem. It's these two invariants in the denominator, and the integrand has what are generically called infrared, or more precisely infrared or collinear singularities. The old-time purists would probably use infrared just to mean the soft singularity, but I'm a younger generation, and so it may not look like that to you. And so I just use infrared to mean infrared, soft, and collinear together. So these are generically log singularities in 4 dimensions, and we can identify where they sit. So the strongest one is, of course, at the corner, where we have both of these scaled invariants tending to 0. And this is a soft singularity. And the other two are along the lines. So if we draw our Dalitz region, then we have the soft singularity sitting over here, and let's label this as YQG and YQ bar G. So this line over here is a collinear region. Maybe I should draw it in a different color since I have all these wonderful colors. So that's the first collinear region where YQ bar G is generic, but YQG is 0, and the other region, of course, is the exchanged region, where YQ bar G is and this is precisely where the quark is collinear to the gluon, and the second one is where the antiquark is collinear to the gluon. So what this is telling us is that the 3-part-time cross-section is the total cross-section is not physically meaningful. an infinite result, a physical observable has to have a finite and well-defined result. Is. So we should step back and think about something that was really understood as far back as the 1930s in a very simpler, in a much simpler context. So let's think about just photon emission in some process, something you can do without any high energy colliders or anything fancy like that. So we're going to have some experiment here. Maybe there's some person here, which I don't know if my graphic skills are suitable for that. And there's a photon that gets emitted, and I guess maybe, I don't know if they had photodetectors in the 1930s, but in any event, there's some photodetector and some wires. And it's going to measure the photons. Now, any physical detector has some threshold. If you have a detector that's sensitive to visible light, and you shine a radio signal at it, it's not going to be able to detect it. So it can't detect photons that are below a certain energy. And in particular, if we have another kind of detector that's sensitive to charged particles, and an electron goes there, it can't actually tell the difference between an electron and an electron that's accompanied by some photon that's too soft. They're really the same physical state. Now, as your technology gets better, then your energy threshold will decrease, but at any given point in time, there's some energy threshold. There's some minimum energy that you're able to detect. And that's actually a very deep thing in a certain sense that at any, no matter how much the technology improves, even in some abstract sense, you always have to imagine talking about some minimum energy. So if we go back to our three parton configuration, then again, if the gluon has too small an energy, then we're imagining now that we have some very small detector that's sitting way inside the proton, so that we don't have to worry about confinement and all the confusion that may engender. And there's some cutoff for that gluon. So if the gluon is too soft, then it can't see it. And so then all it's going to see are the quark and antiquark. So it looks like a two-jet configuration. Similarly, any photodetector, any gluon detector that you put inside this very miniaturized detector that you would imagine putting inside a proton, it has some angular resolution. It has an angular size, and if two photons are too close together, or a photon and electron are too close together, well, in the electron case, it's a massive particle, so it's different. But let's imagine if the quark and the gluon are too close together, they get closer and closer and closer. At some point or other, you're underneath the angular resolution of the detector. And, your technology can get better, and maybe your angular resolution goes down by a factor of 2. But then, okay, so if they get closer by a factor of 2, they still can't be distinguished. So if we have a gluon that's less than some minimum energy, or if we have a configuration where, let's say, the angle of the quark and gluon, the separating angle is less than some minimum resolution, then in fact, physically, this looks like a two-parton and hence a two-jet event. So we really should not be including these configurations when we're doing our integral and trying to figure out what the three-jet cross-section is, or what our simplest approximation to the three-jet cross-section is. So there's another lesson here, and that's that when you are talking about cross-sections of this sort, they're going to be dependent on these resolution parameters. So an intrinsic part of jet physics is that whatever you're measuring, and therefore whatever you're calculating, is going to be dependent on these resolution parameters. Now, the minimum energy and the minimum angle are not Lorentz-friendly objects, so you have to trade them for threshold parameters that are friendly in the context of whatever the experimental geometry is, but the principle is the same. And so we're going to need something that's analogous to a minimum energy to control the soft singularity, something that's analogous to a theta min to a minimum angle to control the collinear singularity. And without any more explanation, I'll just say that in the LHC context, that role would be played by a so-called minimum transverse energy or minimum transverse momentum. And this thing will be played by the role of a delta R, the R parameter, which is a square root of an angle around the beam axis and rapidity. And those they're not Lorentz invariant, but they're invariant to boosts along the experimental geometry. So this, of course, partly solves our problem. We now have to impose cuts. Let's say some minimum in our simple context here, some go back to minimum energy and minimum angle, and then we do the integration, and then instead of infinity, we'll find some logarithm of some invariant divided by the minimum energy times some other logarithm of another invariant, scaled invariant divided by the angle. And so then we have some finite number. We can ask our experimental colleagues to measure this, and we can see how well our approximation is doing. Of course, we know that we can't just arbitrarily throw away some of the configurations. We had our leading order approximation to the two-jet cross-section, but now we've said, oh, okay, some of these configurations that we might have thought are 3-parton and therefore 3-jet configurations, they're really 2-jet configurations. Now there's an additional power of the coupling of G in the amplitude, the 3 final state parton amplitude, so when we square it, it's going to be G squared. After we do the usual renormalization and redefine things in terms of a physical coupling, that'll be an extra power of alpha compared to A2 squared. So this is going to be the next order correction to the 2-parton configuration. So it's going to be part of the approximation to the 2-jet cross-section. So we've maybe resolved our problem for the 3-parton, 3-jet cross-section, but we've just shifted that problem to the 2-parton cross-section. Now, the way we actually do these calculations, so we've talked about dimensional regularization, so let's actually go ahead and see what would happen. We can at least improve on the infinity there by going to dimensional regularization. So what that does essentially, instead of just having dy qg dy q bar g, it multiplies that measure by a factor of each of these invariants raised to the minus epsilon power. And as I've been saying all throughout, for the purposes of infrared regulation, then you should think of epsilon as being slightly negative. So we're multiplying the measure by a small, an infinitesimal but positive power of each of the variables. And you know, of course, that once you do that, then our integral will become convergent. So as long as epsilon is not actually 0, we're going to get at least formally finite result. And so we're now splitting the region, and instead of using E min and theta min, I'm going to use Y min. That's at least Lorentz invariance cutoff. It may not have much to do with what the experiments can do, but at least it's easier for us to deal with. So we're going to do that integral, and now we're going to do it in the region that is kind of left over. So we have our Dalitz plot, and we have some cutoff y min that we're going to put in. And this region, everything is fine. The region that is over here where everything is above the cutoff, this is a proper 3-parton configuration, so it's really a good first approximation to the 3-jet cross-section. It's dependent on y min, of course, but we understand why that has to be so for very solid physical reasons. And I've mislaid orange chalk here somewhere. So I think we want the regions to be pink. That would be a bad idea. So now we're going to do the integral over these regions over here. And modulo some overall constants, some additional constants coming from the integration. This constant is not the same as that constant. Then we're going to get an answer that looks something like this. So again, if we were to take y min to 0, we see that we in fact have not just a single log, but a double log divergence. That's characteristic of soft singularities. The single log that's left over is kind of a collinear survivor. But as long as y min is finite and as long as epsilon is not strictly 0, this is at least well defined. On the other hand, of course, epsilon in the real world actually is 0. So this doesn't fully solve our problem, but at least it helps us organize and kind of regulate our problem. So what is the resolution here? So again, we're now looking at a contribution to the 2-jet or 2-parton cross-section that is one higher order in alpha s. So it's the lowest order actually is independent of alpha s because it depends only on the weak or electromagnetic couplings. And now we get a contribution that's one higher order in the QCD perturbation expansion. So now we should sit and think. Well, I've spent 3 hours telling you how to compute loop amplitudes, and that's not just for abstract interest. It's because these things show up, of course, in the perturbation expansion of our 2-parton matrix element. So there's additional contributions that we have to include. So we can imagine, of course, taking A2, we'll now have some one-loop contribution. We have to square it. That means we're going to get an interference term between the lowest order and the one-loop contribution. And we can write that diagrammatically. So write that as the real part of this thing. And now we still have the Q and Q bar, but now we have a virtual gluon that's exchanged. And this is now something that, this is of course a very simple process, but we know how to write down the integral decomposition. We know how to go about finding, well, this one would involve triangles, so I haven't actually done an explicit example, but the same technology, you could find the coefficients, you could write some explicit formula in terms of the triangle integrals, and once you're through with Professor Doerr's lectures, you'll even be able to calculate them. Actually, the triangle integral is simple enough that you should be able to calculate it in your sleep. And so there's additional contributions, and as I've hinted, there are also infrared singularities. The loop integrals are generically also have poles in 1/epsilon. So one might hope that maybe these contributions will cancel each other and we'll end up with something finite. So, and that in fact is what happens. Let me, in fact, are people happy if I erase this rather than erasing something earlier? Is anyone still copying that down? Okay.
How is delta R called? So you said transverse momentum. And
so transverse momentum is the analog of the energy cutoff, and delta R is the analog of the angular cutoff. And it's just called delta R. This is the rapidity or pseudo-rapidity, and this is the azimuthal angle. And I don't know that there's any, maybe we should start a web contest to have a new name for the flashy new 21st century name for delta R. I'd say it's one of the complaints that non-scientists often have, is that you have all these wondrous things that you do, and then you give them these extremely boring and technically complicated names, and so it doesn't really have any pizzazz. So if you want to start a contest to have a more flashier name for some of the things we've been talking about, then you're welcome to do that. So, what do we need in order to actually analyze this a little bit better? So we need a regulator, which we have, but it has to be consistent for both the virtual contributions, which are the loop amplitudes. So this would be a virtual, this interference term would be a virtual correction to the squared matrix element, and also for the real emission. So when you actually emit a massless particle into the final state, as in A3 up there, that would be called a real emission contribution once we square it. So we need to have the same regulator. It has to treat all the states in exactly the same way. So dimensional regularization certainly treats the momenta in the same way, but you have to use the same variant. Remember that if you open the cover of the box called dimensional regularization, then unlike Alice, you don't find just a single bottle in there. There's many different bottles that have slightly different labels. You got to pick the same one for the virtual and real emission contributions. The other thing that, of course, we have to find is that the divergent contributions should be equal in absolute value is kind of a queasy thing to say when they're poles in epsilon, but the coefficients of the epsilon should be equal and opposite from the two, and generically the virtual ones, at least the leading ones, will come with a negative sign in fact. And this is very non-trivial, because here we're doing some loop integral. Here we've done some phase space integral. We're starting with different numbers of particles. The kinematics are different. So this is a very non-trivial kind of cancellation that we're looking for. And there's a certain sense in which this can only happen if there are certain universality properties. And those universality properties have to hold on the one side for the virtual corrections, and on the other side for the real emission corrections. And this might seem like magic, and to some extent it is magic, and but it's guaranteed. It's a theorem, a very broad-based theorem in relativistic, really in perturbative quantum mechanics. And it relies only on unitarity and perturbation theory. And it goes under the name of the Kinoshita-Lee-Nauenberg theorem, or KLN. And there are actually two separate papers, a paper by Kinoshita and a paper by Lee and Nauenberg. And it's the latter paper, the one by Lee and Nauenberg. It's, I think, a 1963 or 64 paper in Physical Review. I highly recommend reading it. It's a really beautiful paper, and makes it clear it's an extremely general result. And what it says is that if you sum over all indistinguishable final and initial states that gives rise to a finite observable. Doesn't matter what regulator you use. It doesn't really matter the details of the theory. It's a very general result in quantum mechanics, at least in the perturbative expansion of quantum mechanics. So the thing that's a little bit subtle here is the fact that you also have to sum over all initial states. And that's not what we do with the LHC. So for LHC purposes, one needs a much further machinery, which goes under the name of factorization, and then there's questions of surviving collinear singularities that have to be absorbed into the initial state. It's all a very interesting subject, and some of the tools you would need to understand that we're going to see in the next few minutes. Those two pictures up. So we need to find certain universality properties. And what we're looking for is something where we have twice the real part. So now let's think about some endpoint process rather than integrating over everything. We're going to look at some n-jet process in some fully differential way. And so then there's the virtual contributions, which are going to look like this. And then we're going to do a certain integral. But instead of doing it over the entire phase space, we're only going to do it over these I don't, these are not, they're not really connected. I mean, there are, in the sense there's a certain sense in which you can think of the loop corrections as being a delta function distribution that's sitting at the collinear limit that's canceling it off. So if you were actually to construct some distribution of some observable, some physical observable, I don't know, let's say the cross-section is a function of the angle between two jets or something like that, then, and if you were able to do the whole thing analytically, then you could imagine just calculating the real emissions all the way to the end and calculating the virtual corrections all the way to the end. And then there's a certain sense in which the virtual corrections are a delta function sitting at 0. Let's say if you're looking in terms of the unobserved radiation and the physical jet, and that the real emissions are giving you some distribution which then would be singular and cancels off, if you integrate it, cancels off that delta function. So in that sense, you can think of the one loop as being like a distributional term.
If you're taking that specific kinematics, you don't know whether you're going to get those terms.
I'm not exactly sure what Professor Hen was thinking about, but those are not terms that show up in the real world, so I'm not precisely sure what he was thinking about.
So here you took particle 1 and 2 being collinear. What if you had several particles going collinear?
So that's a very good question, and if I had not 4 hours, but more like 10 hours of lecture, we might have gone that far. But the answer is that these factorization properties do generalize. When you have multiple things that are becoming singular, then it's a little bit more subtle because they're intermediate angles that actually survive and then you have to integrate over. But you can think about double soft, two things becoming soft, and there's a similar kind of factorization. You can think about the triple collinear, which is maybe the most immediate generalization of this. And there are analogs of this where you split essentially one particle into three that are collinear, and then it's a function. So it's more complicated because it's not just a function of a single splitting variable. It's a function of two splitting variables and also of some relative angles. And those relative angles are not, they're things, in order to really fully get this factorization useful from a physical point of view, you end up having to integrate over.
Can you use this kind of factorization to get information about the original output loop? In the sense, kind of for constructing it, I don't know, maybe taking the soft limit in 1, 2, and 3, and 3, 4, and...
So, in fact, you can get an enormous amount of information about the original amplitude by constraining its collinear limits. Typically, these days, I would say you use it more as a cross-check on a result than as a means of constructing, because it's hard to do that in a systematic way. Or maybe a different way of phrasing would be to say the systematization of that would ultimately lead you to a BCFW kind of construction. To really do it in a systematic way, you have to be thinking not just about the real kinematics, but about complex kinematics. But yes, if you have some rational function, more generally, even if it's not an amplitude, but only part of an amplitude or some other function, if you know something about its singular limits, then you can, and you have some ansatz for it, you can use that information to constrain the ansatz, and in some cases that gives you a unique answer. So absolutely, you can use that information to reconstruct things. In fact, some of the very early, when we were still working out some of the unitarity ideas, the original n=4 SUSY amplitudes were in fact first guessed really more based on the collinear limits, and then unitarity was kind of used as a proof rather than the cleaner pedagogical way that I presented it here. Yes?
Something that I think was not mentioned also in Johannes Hen's lectures. Generally in BCFW, maybe not in the Park-Taylor formula, but yes, one feature of one peculiar property is that the expression one gets, apart from being able to write it in many ways, they also have spurious poles.
Yes. So that again, I mean, that's a topic. If I had more time, I would have talked about. But since you asked the question, I'm going to take 5 minutes to answer the question, even if it's not really a student question, but kind of a question from one of the organizers. So let me find the formula that I would have written down. Where are we here? Okay. So I showed just one very simple integral here, but let's look at a slightly more complicated integral, but maybe the simplest non-trivial integral. So if we write this is for those of you who are actually taking notes, is known as the easy two-mass box. And so there's an S channel and there's a T channel, and then there's two masses for legs 2 and 4. And we can actually write down a formula for this amplitude. So it has some gamma constants in front, which we don't really care about too much. And it has this very interesting prefactor. And then it has the double poles that, or appears to have the double poles, I should say, that you might have expected from a box integral. We'll see what happens with them in a minute. So that should be minus. And then we have our friend the dilogarithm. And then there's n2 squared over s. And n2 squared over t. And 4 squared over s. 4 squared over t. And then I guess I've run out of space, so I'm going to make you read upwards again. 2 squared and 4 squared over st. And then there's a minus log squared s over t. And then there's order epsilon corrections, which at least next to leading order, we don't care about. So, the first thing is that it looks as though there's a 1 over epsilon squared, but in fact there isn't, because if I take the lowest order expansion here, I get 1 plus 1 minus 1 minus 1, so that's 0. And that, in fact, you can see heuristically makes sense, because in order to get a 1 over epsilon squared, you have to have a soft singularity. To get a soft singularity, you need 3 propagators simultaneously. They can go to 0. Here you can only get 2 at the same time. Basically, they have to be sandwiched around massless legs, and here there's always massive legs that prevent you from building up a triplet. So the worst that you can get is a 1 over epsilon, a single pole, that you would get, for example, from this pair of propagators. You can see that if you expand this out, there will be various single logs divided by epsilon. So that's one comment. But the question about the spurious singularities actually has to do with this prefactor over here. So this is not a physical singularity. It's something that one could call a planar singularity from its spinor factorization, which I won't explain. I'll just say that. Nonetheless, it seems to be sitting here inside the integral, and you're wondering how can, and in fact there's not generally other integrals that can cancel off this singularity. And that's kind of a typical thing that happens in BCFW. You'll get these strange spinor factors in one term in the denominator. In integral functions, you'll get things of this sort. So what happens? Of course, physically, the only kinds of singularities we can have are either factorizations, so they have to be on spinor pairs, or they can be on multi-particle invariance. In the color-ordered situation, it always has to be invariance of a contiguous set of momenta. Something that's not a physical singularity, the amplitude cannot have a branch cut, it cannot have a pole. And so what happens? Well, and I leave this as an exercise, if you actually expand out this function, you'll find that the dilogarithms here, the expansion of the dilogarithms conspires to cancel off this singularity. So in some sense, it's a fake singularity, it's spurious, and it cancels itself out. And one of the ways you can see that, this term actually works out on its own, that the leading term here, of course, is just going to be the argument. Like the dialog starts with a term that's proportional to x, and that term, of course, is just going to be, if you put it on a common denominator, it's going to be st minus n2 squared n4 squared. That's just going to cancel the pole in front. And it's a less trivial exercise, but actually a good exercise in kind of dialogue gymnastics to show that this spurious singularity cancels. And that's a general feature, and again, it's a strong cross-check on any calculation you've done. You can test it either numerically or analytically, that when you see what looks to be a spurious singularity, it has to cancel out in a final physical amplitude. And with that, let me actually release you to the coffee break. Or I don't know if you have any closing remarks you need to make.
No, let's all just thank David Kosower for a very nice